Hello and welcome back to Calculus 2. Even though we will be talking about differential equations rather than Calc 2. So the stream is starting a little bit late because obviously I was stuck in traffic and I am finally here, so let's. Well, he's stuck. No, stuck in traffic is actually not a good excuse, right? Because it's quarantine time. I forgot something at home. No, I'm at home. Whatever. Let's see what we can do with differential equations for today. Now, there are 5 sections in a book. There is a course called Differential Equations, which you guys can take after the Calc 2 is over. And there is, and one more thing that you need to know. Differential equations, the first course in differential equations is still elementary mathematics. Yeah, people will refer to it as upper level math course or something. No, it's not upper level. Differential equations is the basic course that you need for all of your engineering and all of your physics. And in order to solve differential equations, you have to be able to integrate, which means Calc 2. Today, we are going to look at 2 sections back to back and finish off chapter 9. We're only going to take a look at sections 1 and 3. Now, section 1 is teaching you terminology and words and, some of the important ideas of what differential equations are. And then one of the methods of solving basic differential equations is presented in 9.3. It's called separation of variables. That's literally your day 1 of DiffyQ. So what we do today, and you guys, look at these 2 sections. They will be 2 separate videos, so 9.1 and 9.3. That is already added to your homework. So just, go and work on the problems, and we'll go from there. So let's start with 9.1, differential equations. This is the overview. You can also call it intro to differential equations or whatever. The book is calling it basic ideas. Yeah, it's calculus, so obviously it's basic. So let's take a look at the course. As usual, there is a chat, so you guys can stop me when I start making calculation errors. So, hello chat. There we go. And wow, 17 million people watching it live. This is amazing. All right. So, differential equations. What are differential equations? What are good for? Can we live without them? So, let's go. Differential equation is equation which contains independent variable function and its derivatives. The word differential, right, is the word differential means differentiation, right, which means derivatives. Therefore, we must have the ability to solve the equation which has the derivatives inside. So we can write this as f of x, y, y prime, y double prime, go on, equal to, we can technically put 0. That's a specific kind called homogeneous equations. Or we can put, f of x, and we would say this is non-homogeneous, which would be, there is a driving term there, which would, add energy to the system and stuff like that. So differential equations are equations which contain independent variable, and usually that variable is t, because most of the things we are computing are a function of time, right? Calculus is a study of change. Differential equations, just calculus on steroids. So technically, for most of your differential equation course, you should be dealing with the t being time, being the independent variable. So today, eventually, we will get to talk about the population, and that will be expressed in units of time. But before we get there, we need to understand what these equations are. Now, there are a couple of things that you guys need to know before we go and start solving problems. So the first thing is that a differential equation has the order, and that refers to the highest derivative present in the equation. So when we say order, that means highest derivative present. So equation like this, 3y double prime plus 6y minus ty equals to sine t, would be called second order equation or differential equation. Okay, why second order? Because the highest the highest derivative you have is the second derivative. You can have 3x y to the fourth y prime minus sine x, because I started x as an independent variable in this one, equals to 4. This one is the first order, right? And not the first order from Star Wars, the first order differential equation. Here, I'll spell it out. So order. Now we understand what order means. The highest derivative you have is the order of the differential equation. Another thing that we need to distinguish for these equations is homogeneous versus non-homogeneous, and that's again whether it's equal to 0 or not, and that is a big deal. I'll explain that with the pendulum. So homogeneous versus non-homogeneous. Homogeneous would be when f of t y prime dot 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 is equal to 0, and this one is when f of t at y prime y double prime dot 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 is equal to some function, let's put f of x, right? So these are the two worlds. And we are going to take a look at the difference between these two through the example. So if you are to suspend something, right, at the end of the string off of the ceiling, or you can say a child on a swing, that's a pendulum, right? It's suspended, and then you just push the kid and it starts swinging back and forth. So what you do with this system is you lift the system, right? Lift and let go. And never touch it again. Right? So that is the left hand side. So think of the kid, right? You go, you swing the pendulum, right? The kid is on the swing. You pull the kid back, right, and you let go, and you just leave, right? We all know that eventually kid is going to stop swinging, right? Eventually. Now, what is the non-homogeneous case? This function here provides you with the ability to keep pushing the kid every time the kid goes here. You hit it with f of x. So you know that the trigonometric functions are periodic, right? Positive, negative, positive, negative, positive, negative for y's. So you can be behaving like a sine function, right? You are pushing the kid, adding the energy to the system, then nothing happens, nothing happens, nothing happens, then kid is back, then you push it again, and so on, right? So this particular part now with the kid is keep interacting with the system forever, right? So that's the difference between these two, and you should be able to recognize which one it is. And it's simple, right? It's equal to 0, right? So the system is in a motion, differential equation is measuring, doing whatever it's supposed to be doing, and that's it, right? Where over here you are constantly interacting with it and you keep adding the energy to the system or whatever. So that's homogeneous versus non-homogeneous. And now the one that it's the least fun for everyone, right, is the one that we are linear versus non-linear. Now that one is non-linear. Okay, so you are all used to the word linear meaning y equal mx plus b, linear line. Well, this is a little bit more than that. You are not allowed to have more than one function or the derivative per term, and you are not allowed to mix them together. So linear versus nonlinear. Y double prime plus 6y equals to 3 is linear. This term has a single derivative, this one has just a function, we're good to go. 4xy prime minus 2y equals to cosine x, also linear. Well, I'm writing it on a linear side, obviously, right? So it's linear. All of those equations are linear because per term they only have one function, one function y, or one derivative. What are the nonlinear cases? Y prime plus 6x equals to 3. See that term? Yep, it ruins it for everyone. You can also have cosine of y prime plus 3y equals to 9. So actually I'm just going to point into the bad terms, right? The nonlinear terms. So anything, function composition, multiplication or division of the two y's, and so on, all of those are making they're all making your differential equation non-linear. So these are some classifications of differential equations. So when I say later on in our first order linear differential equation, I don't want your head exploding, right? So it's just, that's what it is. Since we're talking differential equations in the Calc 2 class, so we are talking about chapter 9, and we need to know terminology so that we can communicate properly. So even though this is a Calc 2 class, you still need to know this terminology so you can move on with the rest. Now, in blood, again, the solution of differential equation is a function. The solution of differential equation is the function. So far, every single equation you learned, in mathematics up till today, every single equation you ever solved had a number as its solution. X plus 3 equals 5, x equals 2. Okay, move along. E to the x. So e to the x equals whatever. Solution is ln of that whatever, right? You are always able to find solution for the equations, whether it's algebraic or graphical solution, and those solutions would be numbers. But in the case of differential equations, your solutions are functions, and those functions, would be used as models so you can calculate what you want to calculate down the line. So solution of the differential equation is a function. Maybe I should say is a function, not the function, because there is the plus c situation, which stacks infinitely many functions on top. All right, cool. And now we're going to write this. Let's go blue to check your solution. Answer. Differentiate it and plug in into the differential equation. Well, this is the same concept as for regular equations, right? If you have an equation x plus 2 equals to 7 and you solve x equals to 5, to check you plug in 5 plus 2 and you get 7 equals 7 and you know it's correct. Now, it's going to be a little bit more annoying because you will calculate your y, Then you have to take y prime, maybe y double prime, and so on, and plug that stuff in. So we'll get there when we solve some of the basic examples that we have in 9.3. So now, what we are going to do is we are going to learn and understand why is such a big deal, differential equations. Why is that, a thing? Differential equations are responsible for 100% of sciences. That's simple as that. 100% of sciences. All of your equations you have ever used in STEM, all of the equations that you see in physics and so on, they all come from differential equations. Differential equation is the equation that contains function and its derivative. So if you write f equals ma the lame way, you don't have much insight into the concept, right? Especially if you had this on a formula sheet and you never learned anything, right? #education 21st century. But if you write it in a way where you have the derivative for acceleration, wow, a lot of world opens up. By the way, this is why Newton is immortal. I probably already mentioned this in class. You guys know more mathematics than Newton already. That's given, right? He didn't know integration by parts. Trig substitution. Well, trig didn't even exist, okay? Trig didn't even exist. Or exponential functions. They did not exist in his time. You know more mathematics than Newton. Do you know it well? That's a different story. But see, he had the insight of what this means. He wrote this. And that's why he is immortal, right? So when you take a look at this differential equation over here, you have the derivative of velocity. This derivative of velocity tells you that your speed changes in time. Change of speed in time is called acceleration. So in your car, you have two acceleration pedals. There is a gas plus acceleration, and there is brakes minus acceleration. Why? Because both of them are changing the speed, right? So both of those pedals are acceleration pedals. One accelerates, the other one decelerates. In physics, there's just a minus sign on A, right? And you understand that by pushing any of those two pedals, you are changing the speed of the car. Well, that's what this means. Now, speed of the car, right, which is there. Change of speed is acceleration times the mass of the car plus u provides the force with which the car, right, I don't know, hits the tree. Hopefully not, but whatever. So the entire physics and everything else goes from there, right? So you have mathematics to give foundations to physics, and then physics builds everything else. So entire physics relies on differential equations. Now, I'm not going to go into specifics, right? But every equation can be argued that way. Let's talk about the need and the power of differential equations, especially when you use them this way. You observe a system that is changing in time, and you write the sentence in English. You write the sentence in English, And then you translate that sentence into mathematical equation, which turns out to be differential equation, and then you solve it. You get the solution to the differential equation, which grows up to be a formula, right? Which you later on use to compute what you are interested in. So instead of going into the STEM problem, I am going to go into biology problem, the one that it's very easy for all of us to understand, and that one is going to be population. Now, whether we're going to talk about population of bacteria or population of rabbits or humans, that's irrelevant. What we are observing for all of these biological systems on the most primitive scale, I mean, no, I'm not saying that the systems are primitive. We are primitive, but I'm talking about the cheapest possible, the easiest possible observation that we can make. So I'm going and try to keep this sentence in one line so that we can translate it into mathematics, right, in the next line. So I'm going to make observation about population. Now, again, I don't care whether you're talking about rabbits or humans or whatever else. It doesn't matter. What matters is that the most basic observation is that change of population in time is proportional to population. So change, come on, pen. Change of population in time is proportional to population. Again, try to fit this in one line. So change of population in time is proportional to population. Does this make sense? Well, of course. If you're thinking about, we can talk rabbits, we can talk humans, right? If you have 4 humans and you have 4 humans, you have 2 pairs of humans. Then, and let's say, again, simple observation, that humans can only have 1 kid a year, which is, right, 9 months to cook up a baby and so on. So let's say that each pair is able to, so, and no twins, no triplets, no whatever else they have, the 9s and 13s. So you can only have 1 kid a year, and there are 2 pairs of people. Well, that means that the next year there are 6 people, right? So I'm just going to outline this. So if we had 4 people, and let's say those are 2 pairs, right? We'll talk about details of this later. But now we only make 2 pairs, so it's 2 plus 2. This one will produce 1, this one will produce 1, and then when you go to the next year, you are going in with 6, right? Now, for maturity level to produce another human, you still have to wait. I think fertility age is 14 or 15, so you have to wait, let's say 15 years, right, for more pairs to come up. But you know, we don't have to look at that. I just want to take a look that if you start with 4, you end up with 6. If you start with 400, right? If you start with 400, that's going to be 200 pairs, right? And each one of those 200 pairs is going to produce 1 child, right? So 200 of these. So you are ending next year with 500. So see, over here population was plus 2, over here population was plus 100. So you see that change in population, and change is the plus 2 and a plus 100. That's the change, because it's changed from 4 to 6, and it's changed from 400 to 500, right? So the change in population in time was dependent on your initial starting population, right? So if you are comparing United States to China, well, hold on. You can't really compare United States to China, because United States has a population of 300 blah million, 320, let's say, and China has 5 times more, right? So the rate at which China can pump out kids is vastly different than what United States can pump up as a kid. The other thing is this popular epidemic of, looking into Norway and Sweden, and their political and social, dealings, and trying to think, oh, how great would this country be if we adopted that? Really? They have a population of what, 7-8 million? Right? We put that many in one city. You don't get to compare, right? Ever. So it's very important when we are trying to understand what differential equations are, right? You have to observe some kind of a system. You write the sentence that makes sense, right? Like here, right? Change in population is proportional to initial population. And then you go and you translate that into mathematical terms, and you try to solve that equation. So now I'm going to get rid of this. We will come back to these numbers, by the way, because I'll have to explain another feature of differential equations. But right now I am concerned with translation. The change of population in time is going to be change of population in time. Yes, that's the derivative. dp dt is the derivative of population. Then we have the equal sign, the word is. Now, word proportional is going to give us some kind of a constant, say constant k. And finally, we have population over here. That's just going to be p, right, times p. And there it is. dp over dt is equal to kp. This is first order linear differential equation. And we would like to solve this equation because when you look at this situation here, right, you can see that p, which is population in time, is the unknown function, which is what we are solving for, and our independent variable is the time t. So for this particular problem here, t is the independent variable, and p of t is the unknown function. By solving differential equation, we will compute, or we will get, I don't like the word, I hate the word get, I don't know why, I just try to avoid it every time. So by solving differential equation, we will find p of t, and that is our, right, that's our goal. So that's what we are going to get at the end of this problem. So what do we do? Well, 9.3 is reserved for you to learn this method. Separation of variables. And I really don't care if you get it now or not get it, because 9.3 is just teaching you that. So, right, I'm just going to plow through these calculations because we are focusing on something else in this lecture. We are focusing on what they are, definition, right? What they are, what kind of solutions they get, how to check the solution, and this idea that you are transforming the world around you, right, through differential equations into equations which you see in your STEM classes. That's 9.1. 9.3 would be the nitty-gritty of what I'm going to write over here. All right, so separation of variables. When you read that and say it a few times out loud, it immediately should be clear that all of the variables of one kind should be on one side of the equation, and all of the variables of the other kind should go to the other side, therefore separating them one from another, and then you will see, integrate both sides, right? So I have two variables. I have an independent variable t and dependent variable, which is a function p. So put all p's on one side, put all t's on the other. So that should look like this. dp over p is equal to kt. So what I did is I moved the function p to the left and moved the function t, which was dt, to the right. Oops, should say k dt. There we go, k dt. All right. So now we integrate both sides. So we separated variables, and then, right, we did this, and then we just do the integration. This is now simple. We have ln of p is equal to kt plus c. Basic Calculus 1 integration. And in differential equations, if you forget plus c, you're done. You'll see why, but you're done. That plus c is not there for decoration. All right, so we set aside to solve for p alone. ln is bothering it, therefore we are going to e both sides. There we go. And we are going to get that our p, we don't need absolute values anymore because there is no ln, right? Plus, I mean, you're not going to deal with negative population. I mean, what does that mean? What does it mean a population of negative 10? Right? Population of 0 means there is nothing around, right? Population of 1, population of 10 million, but population of negative something, right? So no, we don't need that absolute value. It's a function of time, so you can put p of t. And on the other side, we're going to have e to the kt times e to the c. Now, those of you who forgot the algebra, I'm going to write this x to the m times x to the n is equal to the xm plus n. So we have this side as e to the kt plus c, and then you just split it into two of these e to the exponent, right? So that's what I did, and now I am going to define e of c as p0, which is initial population. So population in time is given as p0 e to the kt. And a whole bunch of you who remember this formula from Pre-Calc 1, Chapter 3, you go, ah, we remember seeing this awful result, right? Well, it's a good result on a short term. It's absolutely awful and abysmal result on a long run. I mean, it's bad. So this over here, as known as the general solution to the differential equation. Now, the word general, there is also particular, we're going to see that later. the word general solution means that you still don't know what P0 and K are and so on. So you just have the formula in general, right? And if you had more information, you'll be able to compute P0 and K, and then you would have what we call particular solution, which is, right? So let's go and take a look at now the features of this equation. So we know that that's a population. So, population in time. You just look up that number, right? Now there's initial population. So P0 is at t equal to 0 at the beginning of time. And the cool thing is you decide when the beginning of time is. If your records for something, for population in a country or whatever, begin at the year blah, 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 you will set that year as a year 0. All right? So let's say that the public records for population started in a particular country started in 1800s. So 1800. Well, in that case, the population in 1800 of that country is going to be initial population, and we will call T00 in that case. And you would start counting and measuring from that point on. That's reasonable. So P0 is initial population. I wrote that already. P0 is initial population, and it doesn't have to mean, right, all the way back in time. There is no all the way back in time. We have been evolving for 5 million years, right? So you don't even get to go back 100,000 years and claim initial population. You can claim your initial population at any time you want, right? As long as the concept obviously existed. You can't go more than 5 billion years ago because there was no planet there. But the idea is that your initial population can start with any value in any year, and then you will call that year 0, and then population that year, and you move on. So that's the first part. Now we get to the interesting part, and that's this K, constant K. So some also call it proportionality constant K. So what should I do? Well, first of all, I want to understand what is K is for, right? Because it's not just there for decoration, right? This is applied problem, and in applied problem, every single letter needs to represent something. E is not a letter, E is a function. So we know T represents time. If you are talking about people, we're talking about in years. Population P0, that's number of people, right? Number of units, so number of people. And population at any time is, again, number of people. So what's K? All right, so K is going to tell us how fast population is growing or declining, right? And that's the one that you have to compute from initial points and other things that we are going to see in some time now. So P0 and K together control what is happening with the population. So to go back to our example, but this time I'm going to work with 10 units on initial population so we can understand how K impacts the calculation, but not just how it impacts the calculation, but how is it related to reality. See, K needs to be either computed or observed and reasoned, right? But you have to have K. So I'm going to start with initial population of 10 people. And look, I said people. I'm not saying pairs. I'm not saying, I just said people. Now, we understand that in human physiology, we need both sexes to make a baby, right? So we need male and female. In this case, right, if this population is all male or all female, your K is 0. And that needs to make sense immediately. Because look at the equation. If K is 0, e to the 0 is 1, so your initial population of 10 people is just the population. If you only have 10 guys and no one else is alive on the planet, well, there will be no new kids, right? Because the gift of creating a life is with a female. Also, if you have all female, 10, well, then and no male, again, no babies. So now we have an issue with, well, it's not an issue. So we understand that K could be 0, and K could be 0 means there is no change in population at all. Okay, does that make sense in our sentence all the way up there? Of course. If K is equal to 0, then you are multiplying whatever population you have with 0, and you get that your change in population is 0. See, so it makes sense not just in the solution, it also makes sense in the sentence that was your initial observation. All right, cool. Now, we understand if all of the 10 people are male or 10 people are female, population will not change in terms of adding new people. Now, if you are concerned with the death rate and so on, and you say, yeah, population will change, but it will go down, say these are all immortal, right? They're all elves, all right? And they live forever, they can't die, and that's it, right? All right, now is time to understand K and be very careful what kind of a K we are choosing so that we can do what kind of K we're choosing for our calculations. So let's say 10 people, and we're going to make a couple of examples over here. So first example is 5 pairs, right? 5 pairs. What does that mean? Male, female, male, female, male, female, male, female, male, female. What do? In a 1 year, they all produce, remember what we said, 1 kid, right? They all produce 1. So what do you have at the end? You have total of 15 people at the end of the year. So that's it. You started with 10, and we don't know what K is. We can compute, but this is something that we need to see that the K, right, has more to it than just all male, right? Now, what I'm going to do is I'm going to say, let's have 1 female and 9 male. Well, remember, female is the one that carries babies, right? So if I have 1 female and 9 male, these guys are going to figure out who's the alpha. We're going to have 1 offspring over here, moving into the next year with 11 people. Right? So you see that you are still starting with 10, like you started here with 10. You started with 5 pairs. You started on the other one with 10 people. And the outcome at the end of the year is different. And now we're going to have 9 female and 1 busy male. That will produce plus 9, right? So now we're going to end up with 19 people at the end. So they all started with the initial population of 10. But the mixture, right? The mixture was different. We had a split of 50-50, and then we had a split of 10 to 9 or 9 to 10, whichever way you want to look at it. But the outcome of the population was different because all of these have the same P0, but K1 is different than K2, is different than K3, because this K, in addition to doing other things, also worries about male to female ratio, right? I think that the latest statistic said that the world has 51% female and 49% male, right? So that actually feeds into this model here, right? Even though we know that not everyone is pairing up and whatever, but the situation is such that, since there is more female, and for increase in population, that is definitely more desirable than having more male and less female, right? Because the female is the one that cooks up a baby at the end. So initial population is a snapshot in time when you start with the population, and then K is the one that deals with the quality of the, how much of the offspring or whatever else. We can talk about, other examples as well. You can talk about Newton's law of cooling when you are using your oven to, bake a cake, or using your fridge to cool off something. In that case, the K, constant K for oven would be, whether the oven is gas or electric or wood burning oven. Also, what else is a factor? What kind of a container let's say you're making a turkey for Thanksgiving. What kind of container is it in, right? Is it an aluminum foil? Is it in a proper, pan? Or is it in, there's just nothing. It's just, you don't do it, but you just put your turkey right on that, on the grill, right? So K will have all of that, and then also the size of the turkey, that also works with K, right? Because bigger turkey takes more time, right? Still population of a turkey and initial temperature and all of that, that's all the same, right? It's just size of the turkey matters, right? So all of these things feed into the K, and K is the one that, it's very, very important. Now, please understand that K, right, was there from the proportionality constant, where the initial population came from your plus C. So now when you forget plus C in differential equations, you're just done, right? You are not going to have any good results if you forget plus C. So make sure the plus C is there. All right, so one of the last concepts that we have to talk about with differential equations is how to check differential equations. So we just had a differential equation given by dp dt is equal to kp, and we had the solution given by p of t is p0 e to the kt, right? So this is what we have for our situation now, and now you want to check, right? Let's say you care, right? You really want to know if you solve the problem correctly. Well, just plug in. All of this mess is P. You have a K, that's right there. So all we need is the derivative of the function to plug it in there. Okay, let's do it. So first off, we find the derivative. So p prime, which is, right, dp dt, whatever, whichever way you want to write it. Obviously, Leibniz is much better, right? If you use Leibniz notation, you are set up for 9.3 separation of variables. This garbage notation here is quick, but you can't do separation of variables there because there is no variable t to separate, right? So we kind of stay from these primes if at all possible. So to check the validity of this equation, I'm going to find the derivative. So looking for the derivative of this, that's a p0 e to the kt times k, because, right, that drops down in a chain rule from derivative. So this works out to be p0 k e to the kt. And now we just plug in. So dp dt equals k times p. This one is p0 k e to the kt. Well, this one is still k. And this one is p0 e to the kt. I hope that you see that p0 k e to the kt is equal to p0 k e to the kt. Right. So it works. Right? Left side equals the right side when you check. This is equivalent to you saying 5 equals 5, right, when you check your basic equations. So we're good. That's it. That's solution checked. Now, in your homework, you're going to have a whole bunch of problems where they give you the differential equation, they give you the solution, and your job is to plug in and verify the answer. So all of the exercises 7 through 16 in the textbook and some other equations here and there, we'll have this. All right. I want to talk about one more concept in this lecture, and then we'll take a break. After that break, we are going to talk about 9.3, which will contain also a portion of 9.1 in it, how to solve initial condition problems. I want to keep that together with, section that actually solves equations. Can't do it here. All right, so the last concept. Last concept is making sure whether your model is good or bad, meaning the solution of the differential equation. Does it really paint the picture of what you are observing, right? And most of the time, we use limit for those purposes, and then we make the argument and see what happens. Now, so this is going to be eye-opening for those of you that are freaking out about the virus going on right now. Pay attention. So, how good is the model, right? So we have mathematical model. We got our population in time is equal to p0 e to the kt, and we say that there is population in time. My population in time. So you go on, you have some numbers there for p0 and k, and you come up with 2022, and plug in 2022, and it says, okay, the projected population of the world is blah, 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 right? How good is this model? How can we trust it, right? Because you probably observed population from 80s and population from 2020 and, in those 40 years, and then you're trying to fit everything for those 40 years. Well, this particular model here, which is our introductory problem for modeling population, is garbage. That's the best way and quickest way to put it. It's garbage. Why is it garbage? It's garbage because when you graph it, right, and you know what the exponential function looks like, the y-axis is population, the x-axis is time, And here's your initial population at time 0. So that's your P0 right there. Now that number there could be 500, could be 500 million. I don't care, right? It's when you start measuring time. What do we see in the limit when you let time go to infinity? What do you see for our model, regardless of what is k, as long as it's positive, right? K and P0 are. You see that population is going to go to infinity. Hell no, right? Hell no. Because the planet has a finite surface area, finite resources. You cannot fit infinite of anything into a finite container. Forget about it, right? So the model is ultimately garbage, right? It's good on a short run. So if you use the last, let's say, 40 years to come up with the mathematical model, and you are going to look, 10, 15, 20 years in advance, yeah, exponential model, what we have here is going to work. But try looking 100 years or 400 years or, it's not going to work. It's simply not going to work. Another thing is that differential equations, and when it's done properly, right, differential equations would give you a value. Now you guys have to take differential equations and learn about these things there, right? They will give you something that is called carrying capacity, right? And carrying capacity will be the limit up to which you are going to grow population. You see, on the planet that has finite amount of resources, finite amount of farmable land, finite amount of clean water, which is less and less every day, when we are stuck on this one planet with finite resources, there is going to be a maximum amount of people that can be sustained in terms of living conditions, food, job, and all of that kind of stuff. And when you go over that number, then there is not enough for everyone, right? And that's not a struggle rich against poor. There is no rich against poor. That is fiction, right? You can overcome all of the issues, and people show that time and time again if you have skill and you actually want to do it. So that's given. But the real thing over here is, what if we were all as smart and successful as Bill Gates? Let's say everyone on the planet. Everyone on the planet is exactly the same because we are all as smart and we are all as successful as Bill Gates. Where do we go from there? Well, we go from there, we rise the population, all of the kids are as smart and as successful, everyone is always as smart as successful. Eventually we are going to hit that line which says, you know what, no more coal, no more oil, no more milk, right? Just no more resources. No more resources, we're done, right? We can't sustain one extra person. And those kind of graphs are called logistics graphs, and they are way more precise. And so this is your carrying capacity over here. You can call that K if you want to. I don't want to use K because we used K as a constant in here. Carrying capacity C or whatever, M, capital M, right? And exponential model will look like this. Here's your P0, and then it shoots up and then levels off, like that. So this is what population would look like. So this carrying capacity here, right, M, would be the max population able to live on Earth. That's it. So that's what that line is. Now, mathematical model that you are going to get for this line is logistic equation, right? P of t, and if I am calculating this, if I'm remembering this well, it will be MP0. I shouldn't be doing this because I am probably going to mess it up. P0 plus m minus P0 e to the negative kt. Yeah, kill me now. I don't have the reference for this with me. This might be it. I am trying to flip through the pages to see if anything similar is given, but it's not. Yeah, let's go with this. I think this should be good. Let me see. When t goes to infinity, e is going to go to 0. It's going to kill this term, and then p zeros are going to cancel, and you're going to get m. This should be good. This should be good. All right. So this is the exponential model. And we see that now, if you let time go to infinity, the system will become stable, and it will hit the carrying capacity m, limiting population, and it's just going to stop there. Because, again, you can't add more because there will be not enough resources for everybody, right? So that's the way it goes. And now it's time to mention the virus. Is it time to freak out? The virus is going and claiming lives, right? Let's see. The status right now, I'm using one of the just random websites to check. Where are we at right now? Terrible information for the class, but it is. We're at 53,000 deaths worldwide. Worldwide, 53,000 reported deaths. It's probably more than that. I don't think that, China and other socialist and communist countries are actually reporting these deaths. Russia and so on. There's no way that there is more dead people in US than China. I mean, China has a population of 5 times, and it started there. So, come on. I mean, they're reporting 2,000 deaths less than US. No way. No way in hell. Our health services are better, our everything is better, and they have a population that is 5 times bigger. And they have the virus for a longer time than we. They're simply not reporting, right? So I don't believe any of the numbers, but all right. Now, none of that is important, as it's important what the death graph looks like. And the death graph looks like exactly like this. The virus is eventually going to kill all of the vulnerable people to the virus. Done deal. No more discussion. The virus is going to kill those who are vulnerable to the virus. This week, next week, in a year or in 2 years, right? Vaccine is eventually going to be there. Yes, we're going to save some lives, but the virus is going to go. But here is the line. I don't know what that line is. That's what the mathematical models are for. That's what mathematicians are working on right now. That's how our federal government is able to provide whatever numbers they're giving, right? And say 100,000, no, 200,000, no, right? They keep changing their mind as the people, mathematicians, are computing. However, those who are naturally immune to this will survive. At one point, the plague killed 2/3 the population, right? That's 2 people out of 3 people, right? Order of magnitude worse than what we have right now. 4 or 5 times worse than what we have currently going on. So when you look at that, the line that you see here, the carrying capacity, is going to say no more deaths. This number of the population is the maximum number that can die from this virus. And you and I are either in this region or in that region, right? That's for us to see once we get it, right? But the idea is that when you're observing, differential equations are what we are looking at to understand the virus. And I'm going to close this lecture by inviting you to look up the YouTube video from Numberphile on coronavirus, where they are solving differential equations on the screen to show you the effects of social distancing, to show you how the social distancing is affecting the rates of infection, why the disease spreads the way it does, and so on. They actually solve differential equations, and they do draw the graphs and all of these kind of things. So please go and find that video on YouTube, watch it, and see the power of differential equations. I will be back in about 5 minutes or less to work on separation of variables, which is 9.3, which will end chapter 9. And I will be, after the lecture, posting announcement to talk about the exam 2, which will have chapters 8 and 9, right? So give about 5 minutes. I gotta switch titles, go drink some water, and I will see you all 7:25 latest. Like and subscribe.